my name's Amna, and in this video I will be deriving Kepler's second and third laws. So let's start off by looking at what Kepler's second law states. He said that the line joining the sun to a planet sweeps out equal areas in equal amounts of time. This implies that as a planet is closer to the sun, it moves a lot faster than it does when the planet is further away from the sun. So to derive this, we have to first define the radial vector as r cos theta in the I hat direction, which is just the radial vector in the x-axis, and that is added to r sine theta in the j hat direction, which is just shown over here in the y direction. So by taking the derivative of this with respect to time, we get the velocity vector as shown right here. And to take the derivative with respect to time, we first do it with respect to r. So we get dr dt cos theta, so cos theta remains constant. And then in the next step, we do the derivative of cos theta, which is minus sine theta d theta dt, and r remains constant. In a similar way, we can take the derivative of r sine theta in the j hat direction, and we get this. Now we can take the cross product of r and the velocity, and we get h, which is a constant vector. So to take the cross product, we can construct a matrix as shown here, and we multiply these and subtract it from the multiple of these two. And that is shown right over here. When you expand it out, you can see that these two will cancel, and this cos theta and sine theta can be combined together, and this can be factored out. And we know from trig identities that cos squared theta plus sine squared theta is equal to 1. So we can substitute a 1 in here, and that leaves us with h is equal to r squared d theta dt. One important thing to note, however, is that the h that we figured out the value for is actually the vector h at any given time, and not the magnitude of h. So to get the magnitude of h, we need to sum up each of the directional components, so I, j, and k, and take their square root. And that, as you can see by these steps, actually leads us with essentially the same thing. This also shows that h is constant at any given time. We're now getting closer to proving Kepler's second law, and we just need to look at the area swept out. This can be done by summing up the area of infinitely thin isosceles triangles of side lengths r that make up the ellipse, and using a small angle approximation to get their areas. So we know that the area of a triangle is given by half times the base times the height. So the base over here is r theta times d theta, or this value, and the height is given by r using the small angle approximation. So the area is half r theta times r theta d theta, which can be simplified to this. Since this is an integral, we can take the derivative of both sides to eliminate it with respect to time. So taking the derivative with respect to time, we get dA dt, and we are left with half r squared t d theta over dt. And we can recognize this as equal to h, which we proved in the last step. And we know that h is constant. So what this shows is that the change in area is proportional to the change in time. We can now begin our proof of Kepler's third law, which states that the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit, or a cubed. To do this, we need to look at the equation of an ellipse, and we can then solve for y, and then integrate to get the area of one quadrant of the ellipse. After we multiply that by 4, because we know that these quadrants are all the same size, and we get pi AB as equal to the area. We proved earlier that this equation represents the change in the area with respect to time. Thus, if we integrate this over one period, going around the ellipse once, we can set it equal to pi AB, or the area of an ellipse. So, then solving for t, the period, we get 2 pi AB over h. Keeping this equation in mind, we can now look at some properties of ellipses and then come back to this to prove Kepler's third law. So this image here shows an ellipse and its directrix over here. And this is the distance between the focal point and the origin, and we'll call it c. We define eccentricity E to be the ratio of this distance c with a. And as you can see here, c is also equal to a squared minus b squared, using this relationship. So this is how we define eccentricity. Now the directrix, we won't go into detail about how the equation comes about, but using these steps and these equations from calculus early transcendentals, we end up with this equation for the directrix. If we multiply these two, you can see that this cancels with this, and we are left with b squared over a. Now moving on, calculus early transcendentals also showed that the radius in polar coordinates can be given by these two equations. This also shows that ED is equal to h squared over gm. And we also proved that ED is equal to b squared over a. So essentially what we've proven now is that h squared over gm is equal to b squared over a. Coming back to the period, which we define to be as 2 pi AB over h, if we square it, we get this value right here. We recognize b squared, just multiplying the a over to the other side, as a h squared over gm. And if we substitute that b squared in over here, we get this right here. And this is what we wanted to prove for Kepler's third law. So now we have shown that t squared is proportional to a cubed.